Let's start. We all know the syllabus, okay? All the thermodynamics is divided into these subcomponents. Thermodynamic systems and properties, processes, properties of pure substances, behavior of ideal and real gas, zeroth and first law, and calculation of, so this is the most important part. Second law, entropy. This is basically GATE syllabus, so entropy is not written in directly. And thermodynamic property charts and tables, availability and irreversibility, thermodynamic relations. Okay, this is the GATE official syllabus. I just broke it down in points. Otherwise, this you will get in a paragraph in a GATE syllabus. But you need to understand what are all the topics that come inside them, and what is important in that topic. That is more important than just reading the topic. Okay. Good evening, Sri Lakshmi. Good evening. Okay, so I hope you are all with me. And next 2 hours we will be together to revise all the formulas for thermodynamics. Okay, so it is just thermodynamics, right? Chalo. Let's start with the first concept of Knudsen number. So we all know we will study thermodynamics by 2 ways, macroscopic, microscopic. And microscopic is a very difficult approach. So what do? We study thermodynamics by using macroscopic approach. Now, how do you know macroscopic approach is satisfied? By using Knudsen number. Knudsen number is defined as mean free path divided by system dimensions. And in order to satisfy the macroscopic condition or the concept of continuum, it must be less than 0.01. It must be less than 0.01. That is why it must be less than 0.01. Okay, and therefore lambda must be less than 0.01 L. Okay, so very small mean free path must be there. Okay, so lambda must be less than the system dimensions. Okay, chalo. Next is Gibbs phase rule. We all know what is the use of Gibbs phase rule. To determine the number of minimum independent intensive properties to define the state of system. If you have to fix the state of system, how many properties? Because there are so many properties. Pressure, temperature, volume, enthalpy, entropy, internal energy. I cannot determine everything. So what is the minimum required properties that you need to define to fix the state of system? That is told by Gibbs phase rule. Okay, P plus N, it is for a non-reactive. There is no chemical reaction. So P is the number of phases, solid, liquid or gas. F is the degree of freedom or the number of independent intensive properties to define the state of system. C is the component. For example, water is a component. Made of more than 2 elements, hydrogen and oxygen. And 2, they are basically fixed properties, for example, temperature and pressure. Okay, so if you do this, you can determine Gibbs number of degree of freedom is equals to C plus 2 minus P. Very important for binary mixtures. For example, at critical point, this formula is not applicable. At critical point, this formula is not applicable. You will use P plus F is equals to C plus 1. At critical point, you will use this formula because I take pressure is constant and is pressure atmospheric. That's why pressure is fixed. Okay, chalo. So by using Gibbs phase rule for a single phase, single component system, for example, ice, water, steam, single phase is there, solid, liquid or gas, and single component. Component is what? H2O. So degree, if I apply this, what do I apply? Single phase means P is equals to 1. And single component means C is equals to 1. So P plus F is equals to C plus 2. F is equals to 1 plus 2 minus 1. So 3 minus 1 is 2. So for a single phase, single component, degree of freedom is 2. I need to define 2 independent intensive properties to fix the state of system. Okay. 2 phase, if phase P is equals to 2 and C is equals to 1, then you will get degree of freedom is equals to 1. It is very important conclusion. Directly objective question you will get from here. Directly objective question you will get from here. Okay, chalo. 3 phase, P is equals to 3 and component is 1. Phase 3, component 1. What is this? Triple point, where all the 3 phases coexist. All the 3 phases coexist and degree of freedom is 0. Degree of freedom is 0. Okay, so very important conclusions are degree of freedom at triple point is 0. Degree of freedom at critical point is also 0. Do not get confused. At triple point, at critical point, degree of freedom is 0. Okay, let's move on. This is also objective question. This is also an objective question. Triple point is a state at which solid, liquid and gas exist in equilibrium. Okay, now it is again an objective question. Triple point is a point. It is a point on PT diagram. On PT diagram, I'll draw this for you. It is something like this. PT diagram, solid, liquid, gas. Okay, and this is triple point. Similarly, on a PV diagram, triple point is a line. Triple point. These are all conclusions, very, very, very important conclusions. Directly they will give you in question. In a PV diagram, triple point is a point, line, square, triangle, whatever. Okay, so triple point is a line. For UV diagram, internal energy and volume, triple point is a triangle. Most of the people do not know this. Most of the people do not know this. Okay, it is a triangle. Let's move on. Ideal gas equation. How do you get ideal gas equation? We combine 3 laws. Boyle's law. We apply it at constant temperature and number of moles. Charles law. Constant pressure and number of moles. So Boyle's law says volume is inversely proportional to pressure. Charles law says volume is directly proportional to temperature. And Avogadro says that volume is directly proportional to N. So if I combine this, volume is proportional to Tn by P. So Vp proportional to Nt and Pv is equals to nRT. This is our ideal gas equation in terms of number of moles and universal gas constant. R bar is universal gas constant. Okay. Now I can also modify this in terms of this, where N is equals to mass upon molecular weight and characteristic gas constant is divided by R upon molecular weight. Very, very, very important. R, you have to remember the value of R. R is equals to, R bar is equals to 8.314 kilojoule per kilomole Kelvin. If they do not give this in question, it is not examiner's fault, it is your fault. So you must remember this. You must remember this. They will expect you to remember it. Okay, chalo, let's move on. What is compressibility factor? Compressibility factor. So I know that PV is equals to mRT, ideal gas equation. PVM is equals to RT. Yes. PV is equals to nRT is what? Ideal gas equation. No. Now this is specific volume RT. PV upon RT is equals to some constant. And this constant is compressibility factor. This is compressibility factor. Now for ideal gas, PV upon RT is 1. So compressibility factor of ideal gas is 1. But for real gas, it deviates from 1. It deviates from 1. And real gas behaves as ideal gas at low pressure and high temperature. Again objective question. Again objective question. When does real gas behave as ideal gas? So at low pressure and high temperature is the right answer. They will say low pressure, low temperature, low pressure, high temperature, high pressure, high temperature. These kind of options they will give you. Okay. Yes, for ideal gas it is 1. Compressibility for ideal gas it is 1. Okay, let us move on. Let us move on. Relationship between Cp, Cv and gamma. Cp, Cv and gamma. Cp is what? Specific heat at constant pressure. Cv is specific heat at constant volume. Gamma is adiabatic coefficient. Okay, so we all know that Cp minus Cv is equals to gamma, and gamma is equals to Cp by Cv, and always Cp is greater than Cv, therefore gamma is always greater than 1. Okay, now by using these two equations, I can define this and this. These are important conclusions that you can directly use in numerical. For example, Cp is given and R is given. Cp is given and R is given, so you can calculate Cv. Or Cv and R is given, so you can calculate Cp. Okay, so very important conclusions. Okay, let us move on. Let us move on. Thermometers, thermometer. So Zeroth law is the basis for temperature measurement. There are 5 types of thermometer, and they have their thermometric properties. Okay, now what are the thermometers? First is resistance thermometer, electrical thermometer, also called as thermistor. What is the thermometer? Again, objective question. Match the following, so you can get from here. Okay, now the resistance is the thermometric property, and it is based on Wheatstone bridge. It is based on Wheatstone bridge. Second is thermocouple. Thermocouple. What is thermometric property? EMF, voltage, potential difference, whatever they can say, and it is based on Seebeck effect. Okay, now the next is constant volume gas thermometer. Volume is constant and gas is there, so you can apply ideal gas equation. So temperature will depend on pressure because volume is constant, Mr is already constant, so temperature will depend on pressure. Pressure is a thermometric property. Okay, now constant pressure. Now pressure is constant, Mr is already constant. Now temperature will vary as volume will vary. So volume is the thermometric property. Okay, now mercury in glass, 1, 2, 3, 4, 5. Mercury in glass. So they can give length, height or volume. You see, the length changes, the length or height changes in the mercury glass. If the temperature increases, so the height changes. So height can be taken as the thermometric property. Okay, chalo. So temperature measurement scale before 1954. Before 1954, our temperature scales were based on 2 reference points, ice point and steam point. Okay, so if you have to find a temperature at a particular X, and a specific property at temperature is given at ice point. Ti is what? Ti is ice point. Ts is steam point. Similarly, Xi and Xx is a thermometric property at ice point. Sorry. And Xs is thermometric property at steam point. Now they will say if X is this much, if X is XYZ whatever, then find T. This type of question you will see. So here we have what? We are talking about 1 ice point and 1 steam point. So our temperature scales are based on 2 reference point, ice point and steam point. Very, very, very important. Okay. And this is the conversion scales. So if you want to convert Kelvin to Celsius, you can do it like this. Or Celsius to Fahrenheit, you can do it like this. Okay? Chalo, let's move on. After 1954, temperature scales were based on single temperature, single reference temperature. What was it? What was the single reference temperature? It was triple point of water, triple point of water. Okay, and this is the formula that you can use. This is the formula that you can use. And again, one of the objective question, 1 Kelvin is internationally accepted as 1 upon 273.16 of triple point of water. Ice point and steam point. Okay, yes. Okay, so this is how they have defined it. I cannot do anything in this. They have defined it 1 Kelvin according to 1 upon 273.16 of triple point of water. This is how they have defined it. I cannot do anything. Okay, chalo. Okay, there's a free ebook for gate preparation to guide you for your gate preparation. Okay, that you can download from the link that is given in the description box. Okay, chalo, let us move on. Now we have come to the next chapter, which is first law of thermodynamics. First law of thermodynamics. Okay. Now we all know that what is energy? Energy is ability to do work or transfer heat. Okay. Now total energy can be divided into stored and transit. What is transit? Which has to cross the boundary. Whenever energy transfer will take place, it will take place in the form of heat or work. Wherever energy transfer will take place, it will take place in the form of work or heat. And whenever I have a system and it has some mass, so it will store mass, it will store the mass, it will store the energy in the form of stored energy. So if I have a system and there are some gas molecules, so gas molecules will store energy in the form of internal energy, kinetic energy or potential energy. But if they have to transfer energy, then it will do it in the form of heat or work. Energy transfer always takes place either in the form of heat or work. Okay, if it is not working, then maybe they will update it. It is not updated. Okay. Maybe it is not updated, they will update it. It's okay. ठीक है, चलो. So a mass stores energy in the form of internal energy, kinetic energy, potential energy. Because we are neglecting kinetic energy, there is no chemical reaction happening in a thermodynamic system. Okay, and if this mass has to transfer energy, it will do it in terms of heat and work. And therefore, even though both are energy, this is also energy and this is also energy. But these are point function. These energies are point function and these energies are path function. Have you ever asked yourself why this energy, while for example, while internal energy is a property, why internal energy is a property and work, which is also energy, is a path function? Why is it not a property? This is also energy, this is also energy. Why one is point function, why is one is path function? Because these energies will only transfer, will only take place when they will go from point 1 to point 2. So they will depend on the path. Yes, I'll provide, Vijaya, I'll provide this PDF, no worries. Okay? So because heat and work will only take place when you go from point 1 to point 2. If you change how you are going from point 1 to point 2, heat and work will change. And that is why they are path function, not point function. Okay. Chalo. First law of thermodynamics for a closed system. What is first law of thermodynamics? Energy in is equals to energy out plus change in energy in the system. Okay. So if I am giving heat Q and work is going out and I neglect kinetic and potential energies, I'll get this. This is the first law of thermodynamics for a process. Now, for a cycle, change in the property is zero because property only depends on initial and final condition. And for a cycle, initial and final condition is same. So change in property is zero for a cycle. So for a cycle, del U becomes zero. For a cycle, del U becomes zero. And you will get this from the first law. So very, very, very important for law of conservation of energy. Yes, only energy transfer takes place. So a lot of students do not know this. This is only applicable to process and this is only applicable to a cycle. is only applicable to a cycle. Okay, so you must understand this. You must understand this. Okay, now this file, this image is very, very, very useful for you. Okay, I have summarized all the work and heat because we are talking about formulas. I am not talking about how to derive. I am not talking about how to prove. I am going to talk about the last formula that we derive. And if you have already done this, then this information is very useful for you. If you have already not made this table, that means you are not making short notes properly. Okay, for all the 5 processes, you need to merge all the data. You need to merge all the data. Okay, and I have done it for you. How does a human body obeys law of thermodynamics? All the bodies, even human body obeys all the laws of thermodynamics. No. So whatever you eat, how are you running? How are you living? Where do you get the energy? By the food. So the chemical energy of food is converted into metabolic energy. And that energy goes into mechanical energy or physical energy. Okay. So that energy came in the form of food. Then your system, your body converted into a form that is useful for your body. Okay. Now that energy that you have gotten by that chemical energy of food, you can utilize to do work. Whatever work. If I am pushing this device, if I am pushing this laptop, then my energy is converted into work. So all the laws are satisfied, no? Law of thermodynamics is what? Energy conversion. Chemical energy came in, it converted into some form. So my body has also mass, no? Look, energy came in, or energy stored. Energy came in the form of food, chemical energy of food. Then it is stored in the form of internal energy. Okay, and then if I am doing some work, then some energy is going out. Even if I am not doing some work, continuously heat is going out. So some energy is anyway going out. Okay. No pressure change in the body. Yes, no pressure change in the pressure. Yes. Okay, chalo. This is very helpful information for all of you. Okay. So we know that we can show all the processes in the form of PVN is equals to constant, in the form of this. Now for isobaric N is equals to 0. Okay. And heat can be given as dq is equals to dh for isobaric. And this is your dw. By constant pressure hai, P take out and integrate by dV, V2 by V1. Okay. And this is the ideal gas equation, and specific heat is Cp. Okay. Isochoric, here N, the value of N is infinity. Heat transfer is equals to change in internal energy because work is zero. And this is the ideal gas equation. This is Cv. Okay. Now isothermal N, this N is 0. Okay. And dW is equals to dQ. dW is equals to dQ because internal energy is 0. Okay. And this is my ideal gas equation. And here specific heat is infinite. So much heat absorbing capacity is there. Whatever heat I am giving, it will keep absorbing. Its temperature will not increase. Okay. So specific heat is infinite. Yes, isothermal is no temperature change. Okay. This is pressure as constant. This is volume as constant. Temperature as constant. Adiabatic matlab Q is equals to 0. And here Q is not equal to 0. Okay. Now adiabatic means N is equals to gamma. Heat transfer is 0. Work transfer is P1 V1 minus P2 V2 gamma minus 1. Okay. and this is the ideal gas equation, and C, specific heat is 0, polytropic, N is equals to N, any N, okay. This is the heat transfer, this is the work transfer, it is same as isothermal, same as adiabatic, only the difference is instead of gamma we have N, okay. This is the ideal gas equation and this is Cp, okay. I'll share this PPT anyway, but this is very important information for you, okay. Chalo, let us move on. Adiabatic is no heat transfer, yes. That's why I said Q is equals to 0. Okay. So first law of thermodynamics for a closed system, all these formulas are there. Little bit variation here and there will be there, but the formulas are this only, okay. For steady flow, for open system, when mass is also entering, energy is also entering, then we have two cases, steady flow, unsteady flow. So steady flow is what? Whatever energy is entering will be equal to energy out. And change in energy in the system will be equal to 0. Okay. So this is your energy in. This whole thing is your energy in. Energy is coming in the form of mass. Whenever mass is entering, Mi, it is bringing some energy with it. And if I am giving some heat, so this is energy in. Also, when some mass is going out, it is taking out some energy with it. This is MEEE. And this system is giving me some work. Some work is given. So this is your steady flow energy equation. But polytropic is a very general process. Look, polytropic is a general process. It is a process. You can show all the processes in the form of polytropic and all the rest of the processes. Look, we have covered only, you see, these are very specific process. But this is a general process. The equation is PVN is equals to constant. Now you change the value of N and you get any process you want. And even all other processes that is not even isobaric, isochoric, isothermal or adiabatic. Any general process. Okay? Chalo. Now if I neglect kinetic and potential energy and single inlet and outlet and steady flow, then I'll get this. So this is your first law of thermodynamics for an open system. Okay. And for isentropic process, which is reversible adiabatic, I can also say that this is work control, open work is, so this is called that open system work. What is closed system work? PDV is your closed system work. Chalo, let us move on. What are the applications? Turbine, compressor, boiler, condenser, nozzle, diffuser, throttling. Okay. So based on all the devices, for example, in turbine, if I neglect the change in kinetic energy and potential energy, if I neglect this, and I say isentropic means no heat transfer, reversible adiabatic, isentropic, then I will get this equation. The same assumptions I'll apply for compressor. I'll get this equation. All these equations will come from this equation only. All these equations come. So whenever you see a question from turbine, compressor, boiler, evaporator, condenser, nozzle, diffuser, heat exchanger, throttling valve, all will be solved by using steady flow energy equation. Okay? Chalo. This is for boiler and this is for condenser. Okay? For nozzle, we assume that inlet velocity is much less than exit velocity and potential energy is neglected. Adiabatic is there, Q is 0 and no work transfer. That is for nozzle. Similarly, for diffuser, I assume that inlet velocity is much greater than exit velocity. Okay, and throttling, so we know already with the environment. Yes, that is true, Sri Lakshmi. That is very true, no? Closed system, only energy transfer, no mass transfer. Open system, mass and energy transfer, both transfer happens. Okay, chalo. Unsteady flow. If you have attended any sessions with me, if you have attended any session on YouTube, on app, whatever it is, I have derived this equation many number of times. And I have explained word by word by word the meaning of each and every term. The meaning of each and every term. Okay. Now, yes. Energy and matter. Matter means mass, right? So, I have derived this equation. I have explained one by one each term, the meaning of each term. And I have told you, first understand the meaning of this equation. Write this equation 20 times, 30 times, 40 times. Unless you are not able to draw the diagram and write this equation by yourself. As long as you are going back and turning the pages and coming back, there is no use. Write this equation at least the number of times that is required that you can write it yourself. That's all. Okay, chalo. Now what is the significance? I'll tell you very quickly. Yes, Sri Lakshmi, that is true. Okay, chalo. So uniform flow or unsteady means mass in is not equals to mass out. Energy in is not equals to energy out. Okay. So, some heat is entering in. होगा क्या? Energy in is equals to energy out plus change in energy of the system. ये हमारी, this is the most general form of first law of thermodynamics. We always start by this equation. This is the law of conservation of energy. Okay. Now what is going in? Some heat is going in. So this is this. Then some mass is going in and taking some energy with it. So this is that energy. The mass that is entering is carrying some energy with it. Okay. Now some mass is going out. It is also carrying some energy with it. This is this energy. And my system is also doing some work. So this is work output. Then, what then? Then the change in the energy of the system. Change in energy of the system is what? E2 minus E1. E1 is the initial energy inside the system. But system may have some mass. That mass could be at some temperature and pressure. So it would have some energy. Similarly, when some mass or energy came, either the energy increased or the energy decreased. So final energy is E2. Okay, so this is basically E2 minus E1 and this is your change in energy inside the system. System ke andar what is the change? Because of the energy in and energy out. So that is unsteady flow energy equation. Okay, what are the examples? Filling of tank, emptying of tank. Okay, for example, some tank is there and you are filling it. For example, initial mass is 0. Initial mass, a bucket, in the bathroom you take a bucket. Now the bucket is empty. Now what you are doing, you are filling in is equals to 10 kg. And you are taking out 5 kg. So the level of water will increase, right? That means the mass inside the system is changing. That is unsteady flow. Mass is changing with respect to time. Okay. Similarly, emptying. If you are giving less and taking more out, then the level of water will go down. So it could be charging of battery, discharging of battery, filling of tank, emptying of tank, filling of bucket, emptying of bucket. So whenever the level of mass or energy will increase or decrease in the system, it will be unsteady flow energy equation. You can use this equation. Chalo, let's move on. Also, there's the rolling gate workshop. I told you the next one is on the 1st November. Okay, so there is a rolling gate workshop that keeps happening. You can also find the details about the next workshop and register yourself by the link that is given. And I hope that link is working. Okay, so I hope that is working. You can get the link in the description box. Okay, chalo. So first law is done. Let's move on to second law. Second law, we have two statements, Kelvin-Planck and Clausius statement. Kelvin-Planck and Clausius statement. What does Kelvin-Planck say? Kelvin-Planck said it is impossible to develop a device that works on a thermodynamic cycle and produces work continuously while exchanging heat with a single reservoir. You cannot produce work while taking heat by a single reservoir because heat cannot be completely converted into work. There will always be some loss. Okay, and this machine, if you can make this machine, it will be called as PMM2, perpetual motion machine 2. So if this is not possible, then what is possible? So do not interact with one reservoir, interact with two reservoirs. What do you mean? You take energy with a high temperature. You take energy with a high temperature, produce some work, and reject some heat at the lower temperature. Reject some heat at the lower temperature. Yes, Sam is there. Rejects zero heat. Yes, perpetual motion machine cannot reject heat. It does not reject. It says whatever you will give me, I'll convert into work. But then second law says you cannot do it. Work is a high grade energy, heat is a low grade energy. You cannot convert low grade energy completely into high grade energy. Okay. How do I calculate efficiency? Efficiency is always defined as desired effect upon required input. From a heat engine, you always desired work output. You desire some mechanical output, Entropy of isolated system always increases or remains constant. Okay, it will remain constant. Let me come on entropy, no, Sri Lakshmi. I'll explain it there. Okay? Chalo, I'll come to entropy as well. Okay, efficiency always desired effect upon required input. What is desired effect for a heat engine? Work output upon what is required input, heat that I am giving Q1. And now if I apply first law here, I do a energy balance. So energy in is equals to energy out. So what is this? Q1 is coming in and W is going out plus 2 is going out. So W, what is W? Q1 minus Q2. I can write Q1 minus Q2 by Q1, or I can say 1 minus Q2 by Q1. This is the efficiency for a heat engine. Okay. Next is Clausius statement. Clausius said, what does it say? It says it is impossible to develop a device that works on a thermodynamic cycle and transfers heat from low temperature to higher temperature without any external input. बिना external energy के you cannot transfer heat from low to high temperature. You cannot do that. But without external input. If you want to do it, do it. But give some external input. Give some external input. Then only you can do it. Okay. So this device is not possible. You simply cannot transfer because what happens naturally? Heat transfer always happens from high to low temperature. If you are transferring heat from low to high temperature, you are going against the nature. You cannot do it. If you want to do it, provide some extra energy. So Clausius statement says this device is not possible. So what is possible? If you want to do it, give some extra work. So this is possible. And these devices are called as refrigerator and heat pump. Now refrigerator is a device that wants to maintain, or that is developed to maintain a lower temperature. The purpose of refrigerator is to maintain the lower temperature. Okay, so refrigerator wants to maintain this lower temperature. Lower temperature than what? Lower temperature than surrounding. My surrounding is at 50 degrees Celsius and my room, because AC is working, my room is at 25 degrees Celsius. So I want to maintain this. So I need to install a AC or a refrigerator. Okay. Now what will it do? It will continuously take out heat and go to the surrounding and send to the surrounding. So heat is getting transferred from low to high temperature and I need to provide electrical power for it. So the desired effect for a refrigerator is the lower heat that I need to take out and send to the surrounding. Okay. Now for a heat pump, the purpose of heat pump is to maintain higher temperature than surrounding. You use heat pumps in winters when outside temperature, outside your home, the temperature is 5 degrees Celsius. But inside your home, you don't want to stay at 5 degree. You want to maintain 25 degree. So what will you do? You install a heat pump. You install a heat pump. So the purpose of heat pump is to maintain a high temperature. Higher than what? Higher than surrounding. Now if you are maintaining 25 degree in the room and outside is 5, that means heat will get lost. You will lose heat from high temperature to low temperature. Heat will continuously go from the room to the environment. Then the temperature will decrease. So what do you need to do? You need to bring that energy back. So for heat pump, you need to give this energy back to the high temperature to maintain that at high temperature. Now where will this heat come from? From the surrounding. From the surrounding. Low temperature surrounding. So in refrigerator or heat pump, heat transfer always takes place from low to high temperature. The only difference is in refrigerator, you try to maintain a lower temperature than surrounding. In heat pump, you try to maintain a higher temperature than surrounding. Okay. So COP is always desired effect upon required input. So for refrigerator, because you want to maintain lower temperature, so you need to take out some heat to maintain that lower temperature. So this is your desired effect and this is your required input. And when you do energy balance, you will get this. For the heat pump, your purpose is to provide heat. Provide this heat to maintain a high temperature. So this is your desired effect upon work and you will get this. So if you do a little bit of modification, you will also get this. This is the relationship between COP of heat pump, between COP of heat pump and refrigerator. Now what is the relationship between COP of heat engine and, efficiency of heat engine and COP of heat pump? This is the relationship. Also, efficiency of heat engine can be written as COP of refrigerator plus 1. Okay. So write this down. These conclusions are very important. Okay. Chalo. Now Carnot theorem came. Carnot theorem, there are two theorems. The first theorem says that if you are working between two temperature limits, if you are working between the same temperature limits, all the heat engines, there are so many heat engines that are working, no one will have higher efficiency than a reversible engine. Okay. So when a lot of heat engines, when more than two heat engines are working between same temperature limits, then the reversible heat engine will have the highest efficiency. Also it says, second is what? Ki when there are so many reversible heat engines are installed between same temperature limits, then all the heat engines, all the reversible heat engines will have the same efficiency. If the temperature difference is same, then the efficiency will remain same for all the reversible heat engines. For all the reversible heat engines. These are two conclusions. Now based on the conclusions that if the temperature difference is same, all the reversible heat engines efficiency will remain same, we can say that the efficiency of the reversible heat engine is independent on the type and the amount of working fluid. You can use any working fluid. If the temperature difference is same, then efficiency will remain same for all the reversible heat engine. So it is independent of nature and amount of working fluid inside the heat engine. It is only dependent on the temperature difference. Okay, so we can conclude this. We can conclude this for a reversible cycle. We can conclude this for a reversible cycle, and therefore for reversible cycles I can say for a heat engine I can use this. So just now I have defined that Q1 by Q2 is equals to T1 by T2. Very important information here is that if I say efficiency is equals to 1 minus Q2 by Q1. So I can use this anywhere. Whether a reversible heat engine is there or a real or a irreversible heat engine is there. But if I say efficiency of heat engine is 1 minus T2 by T1, then it is this formula I can use only for reversible heat engine. Only for reversible heat engine. Similarly, for COP of refrigerator, I can write this. Now this you can only use for reversible refrigerators. Okay, and this is for heat pump. This is for heat pump. Q1 upon Q1 minus Q2. Okay, chalo. So now we have come at entropy. Came at entropy. So Clausius theorem क्या कहती है? What does Clausius theorem says? Clausius theorem says that the cyclic integral of dq by t for a reversible cycle is equal to 0. Cyclic integral of something which is dq by t for a reversible cycle is equal to 0. Okay, so Clausius theorem says that there is a quantity dq by t. There is a quantity dq by t, and for this quantity cyclic integral is equals to 0. And in the very beginning of thermodynamics, when we define property, what do we say for a cycle? For a cycle, change in property is equals to 0. The cyclic integral of a property is 0. And now Clausius theorem is saying there is a quantity whose cyclic integral is equals to 0. So I can say that this is a property. This quantity dq by t is a property. dq by t is a property, and I have named this property as entropy. I have named this property as entropy. Okay, so and only for reversible it is true. ds is equals to dq by 2. Only for reversible. Okay, chalo. Now Clausius inequality says that for a cycle, cyclic integral of dq by t will be less than equal to 0. Cyclic integral of dq by t will be less than equal to 0. Why? Because this is 0 for a cycle. Change in property for a cycle is 0. Okay. For any cycle, it will be less than equal to 0. If the cycle is reversible, I am not aware with your issue, Akansha, I am sorry. Okay, this you have to contact. I don't know who to contact. You have to contact the You can just call at the customer care or something, I don't know. Okay, so they will tell you. I don't know about this. Chalo. So Clausius inequality says that cyclic integral of dq by t is less than equal to 0. For a cycle, this will always be less than equal to 0. Now this will be equal to 0 for a reversible cycle. This will be equal to 0 for a, these are very important conclusions. Entropy measure of possible arrangement of atoms. Yes, that is true. That is true. Entropy is a measure of possible arrangement of atoms. You have written it in a very, unconventional way, but that can be said, yes. Because if the possible arrangement change, then disorderness will come and entropy will change. Okay, chalo. Because entropy is the measure of randomness and disorderness in the system. Okay, chalo. So for a reversible cycle, cyclic integral of dq by t will be 0. For an irreversible cycle, it will be less than 0. It will be less than 0. But this is the condition. This is the condition that will tell you that your device, that your cycle is even possible or not. Why this condition is there? This condition will tell you if I will give you a device. I will give you a device कि I have this device and this device is taking this much heat and providing you this much work at this temperature. Now you will apply this and see if it is satisfying this. Then you can say, okay, this device is possible. If it is not satisfying this criteria, then that device is impossible. There is no use in putting money in that device. Okay, so it is if cyclic integral of dq by t is greater than 0, then there is no point in even discussing your device. That device is impossible. I'll come to you, I'll say I have this device, I have a heat engine and it is taking this much amount of heat at this temperature, and you want to know that sign, how do you want to take the sign of heat? Heat transfer to the system is positive. Heat given to the system, is that what you are asking? dq is positive if you are giving. If it is going out, dq is negative. ठीक है? So cyclic integral of dq by t अगर greater than 0 है, if it is greater than 0, then there is no point in discussing. That device is not possible. That device is not possible. Now, for a process, abhi we have seen for a cycle, this is for a cycle. For a process, Clausius inequality, it says that cyclic integral will be greater than or equal to dq by t. Cyclic integral ds, change in entropy, will be equal to or greater than dq by t for a process. ये है for a process, this is for a process. If there is a reversible process, then it will be equal to dq by t. ds is equal to dq by t. If it is irreversible, then it is greater than dq by t. ds is greater than dq by t. So ds is bigger, dq by t is smaller. So I need to add something in dq by 2t to make it equal to ds. What is that? Entropy generation. It happens because of friction. It tells you that your system is irreversible. For a reversible system, entropy generation is equals to 0. What why? Why? What are you asking why for? At least tell the question. No, so many things I have told since then. Why for what? What why? Tell me, I'll tell you what why. Chalo. So, this entropy generation, there are two types of entropy. You see, if I have a system, the entropy will be changed because of two things. What? One that is generated inside the system, entropy generation, and one which happens from the boundary, entropy transfer. Entropy transfer. How will the entropy be transferred? If you are transferring heat dq through the boundary, then because of this dq, entropy of the system will change. And because of inside the system, what is happening? Friction is happening, electrical resistance is there, viscosity is there. Because of all those reasons, entropy generation happens. So entropy increases because of two reasons: entropy transfer through the boundary and entropy generated inside the system. Okay, so entropy transfer and change in entropy happens because of entropy transferred through the boundary plus entropy generated inside the system. Okay, and entropy transferred is called as external irreversibility. External irreversibility. And what is generated inside the system is called as internal irreversibility. Internal irreversibility. Okay, chalo. Now, how to calculate entropy change in a system? Entropy change in a system. So, I have already told you that a system, when a system is undergoing a process, this is for a process, right? This is for any process. So, when a system is undergoing a reversible process, when a system is undergoing a reversible process, ds will be equal to dq by t, and this will be equal to r. This is 0. This will be equal to 0. Okay. No, this is not 0. Okay. So ds is equals to cyclic integral of dq by t. Now there are two cases. What? Reversible isothermal heat transfer. For example, I have a system. I have a very big system, so much heat, and I'll transfer some heat Q. But the temperature is not changing. The temperature of the system is not changing. For example, our atmosphere. So whatever heat you give to the atmosphere or whatever heat you take from atmosphere, the temperature of atmosphere is not going to change. Okay. So how will you calculate entropy in that case? Or for example, take a case of a sea, ocean, or a water. A lot of water is there. A lot of water is there. You keep giving heat. The temperature of water is not going to change. So when these type of heat transfer will happen, so what will you do? Because temperature is constant, so you will take temperature out and then you integrate, and then what will you get? Look, ds is equals to integration of dq by t. Now I am saying when the heat transfer is happening, it is happening at constant temperature. Reversible isothermal heat transfer is happening. In this particular case of isothermal heat transfer, temperature is constant, so I will take temperature out and I will integrate dq. Okay. Now I can do it. What? I can use q by t. When I integrate q, I will find mc dt by t. Something like this I can do. Okay, ds. No, temperature is not always constant. Temperature, it's not a necessary condition. I am saying if temperature is constant, when I am giving heat or the system is giving me heat, but the temperature of system is not changing, in that case you can use this. In that case you can use this particular formula. Okay. Now what if the temperature is changing? So isothermal heat transfer. When the temperature is changing, then what will you do? You cannot take temperature out. Okay. So in this we have two cases. What? Reversible non-isothermal heat transfer. We have two cases. First case is solids and liquid. Okay. So now we have ds is equals to dq by t, initial and final. Now temperature is not constant. Now my system is giving me heat and its temperature is changing. So I cannot take temperature out. So I'll keep temperature inside. I'll do mc dt. Q is what? Q is mc dt, right? By t. Initial to final, and I'll find mc ln T2 by T1. That is how you can find out heat entropy change in a reversible non-isothermal heat transfer in solids and liquids. So solids and liquid ke liye you have to apply this formula. You have to apply this formula. Okay. But for liquids, for ideal gases, solids and liquids ke liye you can apply this. For ideal gas, what happens? dq is equals to du plus pdv. Okay, and dq is equals to dh minus vdp. So it is a function of temperature and pressure and volume. Okay, so I'll do the same. I'll substitute ds is equals to dq by t, and dq I'll replace once by this and second time by this, and I'll get these two equations. It is in the case of non-isothermal heat transfer. Non-isothermal heat transfer. Okay? Chalo. Increase in entropy principle. What does increase in entropy principle says? That the change in entropy in an isolated system, will always be greater than or equal to 0. Okay? For isolated system, change in entropy will always be greater than or equal to 0. I think someone was asking this, isn't it? Who was asking that? Someone was asking anyway. Chalo. So, for an isolated system, change in entropy will always be greater than or equal to 0. Okay. Now, isolated system is what? Universe, which can be said as system plus surrounding. Okay. So you can also say entropy generation or entropy change in a process equal to entropy generation is equals to change in entropy of isolated system will be equal to entropy change of system plus surrounding will be greater than equal to 0. Thank you, Vishwajit. Thank you so much. Why first time? Come, आया करो बार बार. Keep coming. चलो. For an isolated system, entropy change will always be greater than equal to 0. Okay? If it is reversible, it is equal to 0. If it is irreversible, then if the process is reversible, then it is equal to 0. If the process is irreversible, it is greater than 0. So someone was asking this. I hope that they got the answer. Someone was asking this, right? No, not yet. I'll have it. I had classes from evening anyway. Chalo, theek hai. So the entropy of an isolated system can never decrease. Entropy of an isolated system can never decrease. Either it will remain constant. लिखा भी हुआ है. Either it always increases or remain constant only when the process is reversible. It will always increase or it will increase in the case of irreversible and it will remain constant in the case of reversible. Okay, this is called as increase in entropy principle. ठीक है, चलो. Now entropy change. So first of all, understand this. Entropy change of universe always increases. Always increases. Entropy change of universe always increases. Now let us see if the entropy change for a system always increases or decreases or remains constant. Okay. Welcome, Hemant. Oh, amazing session. Okay, thank you so much. Chalo. Entropy change for a system. Now, if I have a reversible process, look, entropy change can be given by dq by t reversible plus entropy generation. Now, if I am talking about reversible process, then entropy generation will be equal to 0. So, I only have this for a reversible process. For a reversible process. Now, I am saying reversible heat addition. That means I am adding heat. So if I am adding heat, means dq is going to increase. That means entropy is going to increase. So ds will increase. Entropy will increase. S will increase. Okay. S will increase. And S2 is greater than S1. Okay. Then reversible heat rejection. I am taking out heat. Now dq is going to decrease. So entropy is also going to decrease. So S will decrease. That means final entropy will be less than initial entropy. And reversible adiabatic means no heat transfer. So no heat transfer, it is 0, and ds is equals to 0. Means entropy will remain constant. It will remain constant. S1 is equals to S2. So in a reversible adiabatic process, entropy remains constant. And when the entropy remains constant, that process is called as reversible adiabatic. That process is called as isentropic process. Okay. So entropy change for a system undergoing reversible process may increase, decrease, or remains constant. It is very important to distinguish between, look, entropy change of universe is always greater than equal to 0. Universe entropy will never decrease. It will either increase or remain constant. But for a system, it may increase, it may decrease, or it may remain constant. For a system. But if you add system entropy and surrounding entropy, then it will only and only increase. Okay. Now entropy change for a reversible adiabatic process is 0, and that's why it is called as isentropic process. So reversible adiabatic process is called as isentropic process. Okay, chalo. So it was the case of reversible process. What happens in an irreversible process? So in irreversible process, ds is not equal to 0. And entropy generation is a positive value. It is always greater than equal to 0. Entropy generation is always greater than equal to 0. It is a positive value. Okay. Now I am saying irreversible adiabatic. Adiabatic means dq is 0. So if dq is 0, ds will be equal to entropy generation, which is positive. That means entropy will increase. Entropy is going to increase. Okay. Now irreversible heat addition. Now you are adding heat. So now you are adding heat means dq by t is going to increase. So this will increase, and this is also a positive value. So this is also positive because it is increasing. So you will get a positive value, and I can say entropy is increasing. Now heat rejection. You are rejecting heat. So now you are rejecting heat means this is always positive. So now let's see, when you are rejecting heat, so this will decrease. But it is a positive value. So let's say this is this big. So if the decrease in entropy due to heat transfer. Because of this, entropy will decrease. Now, if this decrease is less than the increase because of entropy generation, because of heat transfer, you are taking out heat, so entropy is going to decrease. But because of friction in the system, entropy is going to increase, entropy generation. So, if the entropy change due to generation is more than this, so you will get a positive value, entropy is going to increase. But if the decrease in entropy because of heat transfer is equal to increase in entropy, is equals to increase in entropy because of heat generation, because of entropy generation, then it is 0, means entropy 1 is equals to entropy 2. It is entropy will remain constant. ठीक है? And finally, if the decrease in entropy is very large, but the increase in entropy, look, this is constant only. Okay, if the decrease is more, then it will be negative value and entropy will decrease. Okay, so you need to remember one thing. What? All adiabatic process are not isentropic. You see, this is irreversible adiabatic, but entropy is increasing. So all adiabatic processes are not irreversible. Only reversible adiabatic process are isentropic process. Only reversible adiabatic process are isentropic process. But there can be a isentropic process which is not reversible adiabatic. You see, this process, this is not reversible adiabatic, but it is isentropic. Entropy is constant. So, all isentropic process are not reversible adiabatic. These are all objective questions. Okay, let us move on. Okay, so there is also a scholarship test. People who have financial issues and they want to prepare for GATE exam, we provide up to 90% scholarship to register for the scholarship test. I think it is in every 15 days. So to register for the next test, you can go in the description box, you can find the link, register yourself and take up the next exam. Okay? My voice is gone. Chalo, available energy. What is available energy? The maximum useful work that you can take out from a system, from a cycle is called as available energy. Okay, chalo. Available energy in a cycle. So if I have a cycle, maximum work that I can get is available energy. Where will I get maximum work? In a reversible cycle. Okay, so W max efficiency in a maximum efficiency is how much? 1 minus T naught by T1. This is maximum efficiency. It is also equal to W max upon heat transfer. So from here I can calculate W max is equals to Q1 1 minus T naught by T1. Okay? So this is your W max. This is the maximum available work that is there. Okay? So if I modify this and I also know Q1 minus T naught Q1 by T1, and what is ds? It is Q1 by T1 only, no? So I can replace this by this. So I'll get this. If I rearrange, so this is what I am giving to the system. This is what I am giving. This is the available energy. So what is this? Unavailable energy. What is unavailable energy? The part of the low grade energy that cannot be converted into mechanical work. You cannot do anything about this. There will always be some unavailable energy according to second law of thermodynamics. You cannot do anything. So the part of energy that you cannot convert into work is called as unavailable energy. Thank you, Shri Lakshmi. Chalo, let's move on. Okay. So this is unavailable energy and this is available energy. Okay. Now there are so many people who are confused about available energy and availability. Available energy and availability. Some people will tell you available energy is for a cycle, availability is for a system, for a process. Basically, availability and available energy, they are same thing. They are same thing. Okay. So now available energy for a closed system. For a closed system. Okay. So what is this? This is the work. Useful work, maximum useful work is basically the work that you can get, the maximum work that you can get, and the work that is lost to overcome the surrounding. Okay, so this is the work that is lost to overcome the surrounding. Okay, and this is the maximum work that you can get. Okay, now W max will be this minus this, and this is called as availability function for the closed system. Availability function for the closed system. Availability is greater than or equal to available energy. I am telling you that available energy and availability is the same thing. It's not different. Look, available energy, availability, exergy. Okay, I don't know, I think I am forgetting something also, but these are all one and the same thing. These are all one and the same thing. Yes. Okay, now availability function, what does the availability function give you? That you cannot, in a closed system, you cannot get useful work more than this. You cannot get maximum work more than this. The difference of two availability functions. Okay. Yes. ठीक है. चलो. Okay. So this is for closed system. This is for closed system. For open system we have H1 minus T naught, and this is called as availability function for a open system. Availability function for a open system. Okay. चलो. Second law efficiency. What is second law efficiency? First law efficiency only tells you how much is the conversion. Okay. First law efficiency tells you क्या? कि if I am giving heat Q1, only this much portion you are converting into work. For example, efficiency is 90, not 90%. For example, 60% is there. So out of whatever heat I am giving you, only 60% is converted into work. But second law tells you which engine is more efficient. Okay, which engine is more efficient? You are you are saying 60% is efficiency. For a given temperature limit, 60% is efficiency. But second law is going to tell you how close you are from the ideal cycle. How close you are from the ideal cycle. Okay, so it compares your engine performance, it compares your efficiency with the ideal efficiency. It compares your efficiency. Actual is, I told you 0.6, but it is going to compare it with the ideal one, and then it will tell you that how efficient you are. So it is a method, it is a parameter to compare more than two heat engines. More than two heat engines. Okay. So it is Q actual and efficiency actual upon efficiency maximum. What is efficiency actual? Efficiency actual is W actual upon Q1, and this is W maximum upon Q1. For the same heat transfer, I can write W actual upon W maximum. Okay. So it compares your system's efficiency with the maximum possible efficiency, ideal efficiency. Okay. It provides information about how efficient your process is. Okay. Chalo. Now let us come to the pure substances concept. Second law is done, entropy is done, and availability and irreversibility, available energy is done. Okay. Now enthalpy and little small topics are left. Okay. So if I'll give you this diagram, how will you calculate enthalpy? So first, this is subcooled region. Subcooled region means where we have liquid only. This is liquid plus vapor, and here we have vapor. This is critical point. Okay. Now, if I say I need to calculate enthalpy, and what will they give you? They will give you this HF and HG. They will give you this in question. Now, how will you calculate? If I say calculate enthalpy here, so you will put HF means this. You need to calculate it here. This is your H1. And you know this HF. So if you have to calculate this, you need to subtract something. You need to minus something from HF. Okay. So HF minus DH. What DH? This DH. And this DH is what? Cp T saturation minus T1. This is my T saturation, and this is my T1. Okay. Now how will you calculate enthalpy if you are somewhere in between, inside the curve, inside the vapor dome? How will you calculate enthalpy? You will calculate H2. Now I need to find out here H2. And if I compare with HF, then I need to add something to HF. Because H2 is more. So I need to add something to HF. So HF plus X, which is dryness fraction. So X is equals to mass of vapor upon mass of vapor plus mass of liquid, and this is HFG. Hg minus HF. Can anyone tell me what is the latent heat here? What is the enthalpy of vaporization here at critical point? What is the enthalpy of vaporization? What is the H2? This is enthalpy of vaporization. HFG is enthalpy of vaporization. Can anyone tell me what is the enthalpy of vaporization at the critical point? At the critical point, how much is the enthalpy of vaporization? Enthalpy of vaporization at the critical point is 0. You see, as you will go up, this is your enthalpy of vaporization. This is your enthalpy of vaporization. Yes, Sri Lakshmi said 0. Yes. So as you are going up, this distance is decreasing. So your latent heat of vaporization is decreasing, or enthalpy of vaporization is decreasing. At the critical point, both the curve will meet and there is no distance. So enthalpy of vaporization is 0. No energy is required to convert liquid into vapor or vapor to liquid. Okay. Now at point 3, for example, here, at point 3, how will you calculate H3? you need to add something to Hg. Add something. How? What will you add? You will add this dH, which is CPV this. Very important information here, that this is specific heat of liquid at constant pressure. This is specific heat of vapor at constant pressure. CPV constant specific heat of vapor at constant pressure. Okay, chalo. How will you calculate entropy? How will you calculate entropy? Same thing. If I need to calculate here S1, so I need to add something to SF. I need to add something to SF. Okay. So when I need to add something, so I'll do, I think this will be add, right? CF, yes. Okay. So SF, no. I need to subtract something. Of course I need to, it is, S1 is less. S1 is less than SF. So I need to subtract. Okay. So SF minus change in entropy. S1 is equals to SF minus change in entropy. And how can I, this is dQ by T. And then I need to integrate, so I'll get this. Okay, so I can write this. Now how will I calculate if I am at this point 2 inside the vapor dome? So S2. So I need to add something to SF. I need to add something. Okay, so SF plus X, which is dryness fraction, into change in entropy. Okay, so you can calculate by using this formula. At saturation temperature, yes, it's not necessarily 100 degrees Celsius. If you increase the pressure, then the temperature will increase. So whatever energy you need to provide to convert a liquid into vapor at any pressure and temperature, it is latent heat. Latent heat simply means temperature will not change, only pressure will change, only phase will change. Okay, now superheated means you are somewhere here. So you need to add something to Hg. So I have added something which is ds. Okay, so this is how you can calculate entropy. Now, very important relation for a reversible adiabatic process by ideal gas. You can only apply this. Only apply this for isentropic process. When ideal gas is undergoing so many students just go and apply it anywhere. You cannot do that. First, see if it is ideal gas. Then first see it is gas. Then see it is ideal gas. Then see is it reversible adiabatic. Then only you can apply these two equations. Okay. So T2 by T1 is equals to P2 by P1. Gamma minus 1 by gamma is equals to V1 by V2, gamma minus 1. Okay. So these conditions, ideal gas and isentropic, must be satisfied. Only then you can apply these equations. Be very sure that it is an isentropic process, compression, expansion, whatever it is, but it must be isentropic. Okay. Chalo. So ideal gas equation. So equation of states क्या होती है? How can you determine the state of the gas? Okay. So at low pressure and high temperature, the gases follow. If any real gas is at low pressure and high temperature, then it is going to follow ideal gas equation. Ideal gas equation. Okay, and the ratio, the compressibility ratio will be 1. As pressure increases, the real gases deviates from the ideal gas relation, and Z is no longer equal to 1. It deviates from 1. It deviates from 1. Okay. So then what will you do when it deviates from 1? Then in the question they will give you some relation between pressure, volume and temperature. They will give you some relation. You are not supposed to remember van der Waals equation. They will give you some equation, but at least okay. That was the whole objective of this session anyway, but chaliye. Okay. So what will happen if it deviates from ideal gas behavior? Then it will follow other. So you see, pressure, volume and temperature are related like this for ideal gas. But if it is going to deviate from ideal gas, then what will happen? Pressure, volume and temperature will not relate like this. It will relate in a different way. For example, pressure, volume and temperature are related by something else. But you are not supposed to remember this. If they want you to use any other equation, if they want you to use, they do not want you to use ideal gas equation, then they will give you a relation between pressure, volume and temperature. You have to use that relation. But just for your convenience, at least remember van der Waals equation. At least remember. Okay. So then you will use this. A accounts for the existence of mutual attraction between the molecule. It is the force of cohesion. Accounts for volume of molecules known as co-volume. Okay. So when ideal gas behavior is not satisfied, pressure, volume and temperature are related in some other way. Those equations are called as equation of states. The most common equation that we use is van der Waals equation. There are other equations as well, but you are not expected to remember them. Okay, chalo. And finally, we have come to Maxwell relations. And finally, we have come to Maxwell relations. So these are thermodynamic relations. Yes, these are thermodynamic relations. Okay, this is the last chapter which no one studies. And if you see that in the last 2-3 years, they are asking these relationships. They are frequently asking. Most of the students do not study this. And today only I was checking the data for thermodynamics. In last 2-3 years, they have started asking this specifically. So what you need to do, you need to remember these relations. There are proofs for it, but I would not ask you to derive them and remember them. Okay, so write them many number of times so you can prove this. There are proofs for it. Of course there are proof, but you are not expected to prove every time. Okay, so these are first, even I don't remember them. I don't know. Even I don't remember them. I have to go and check. Okay, but my work is done. I can afford not to remember. Okay, so these are 4 Maxwell relationships. Okay, at constant volume and temperature, at constant pressure and temperature, how other properties are related, and this constant entropy and volume and S and P. And these are first and second TDS relationships. Okay, so for the very first time you have to derive them so that you know the importance, you know the concept behind them. But please do not derive every time because there is no use of the derivation. At least for the first time derive it, then note down these equations and keep revising them again and again. Okay, this is the trick. Okay, so I think this is all from my side for thermodynamics. Okay, and for sure it's very important that you join test series to analyze your performance, to analyze your level where you are in your preparation journey. Okay, join the test series, join the test series and test your preparation level. Okay, so BYJU'S is also giving test series. If you want to join, please join BYJU'S test series and attempt the full length mock test and subject wise test and part test. Okay, chalo. Here I would say goodbye to you. Thank you so much for being with me for all this time. I hope you all had a good session. I hope you all had a good revision of all the important concept and the formulas of thermodynamics. Make short notes. It's very important that you make short notes. Write all the formulas in the short notes. 1 or 2 points about those formulas. Okay? Because at the end, only the short notes will be with you to revise. You cannot revise the long notes. Okay? Chalo. So I'll say goodbye. I'll see you in the next session. I think on 22nd we will have a marathon for HPCL. Okay? 22nd, I think I'll see you again. Tada, bye bye. Good night.